Section 1.1 takes a look at exponent properties and how we can simplify complex exponential expressions. But first, before we start simplifying, we want to make sure we review what exactly those properties are that we saw in our previous math experience. To set these up, first I want to consider, let's look at a squared times a cubed. A squared times a cubed. A squared means there's two a's multiplied together, and a cubed means there's three a's multiplied together, which means total multiplied together we've got 5 a's. And what you'll notice there, and hopefully you remember from your algebra experiences, that when we've got two bases that are the same, a to the m times a to the n, what we want to do is we want to add those exponents together, m plus n. So this is our first exponential property, adding exponents from the same base. Now we can extend that a little bit with division. Let's take a to the fourth over a squared. Again, we'll recognize that as 4 a's in the numerator and 2 a's in the denominator. And what we'll see happen is when the a's divide out, we're just left with 2 of them, or a squared. This helps us recall the property that when we have a to the m divided by a to the n, what we will do is we will subtract those exponents. So our second property says with division, we subtract exponents. Third property that I want to remember is when we've got something like a cubed over a cubed. Now, if we use that subtraction system, if we subtract 3 minus 3, we get a to the 0 power. But to help us really understand what a to the 0 power is, let's simplify this the same way we simplified before, with 3 a's in the numerator and 3 a's in the denominator. We'll see that all those a's will divide out, and when everything divides out, the answer that we're left with is simply 1. This tells us the important property that any base to the 0 power is always equal to 1. Our next property we're going to look at is going to set up pretty similar to this. Property number 4, we're going to look at a squared over a to the 4th power. Now, if we use our subtraction rules, that'll give us a to the negative 2. But to really help us understand the significance of this negative exponent, we'll consider 2 a's in the numerator and 4 a's in the denominator. And we'll see when they divide out, what's left is a squared in the denominator and a placeholder of 1 in the numerator. This tells us that a negative exponent, a to the negative m, simply means we move it to the denominator, and we get a to the positive m. I want to notice that the negative exponent did not make the fraction negative. Negative exponents never make anything negative. Rather, the negative exponent simply moves it to the denominator as a positive exponent. Another property comes from if we have a cubed and then the whole thing is squared. A cubed means we have 3 a's, and squared means it appears twice, which means in total we have a to the 6th power. You'll recall the exponential property that says that if we've got a to the m power and all that is raised to the n power, we simply multiply those exponents together. So a power to a power, we multiply the exponents together. Number 6. If we've got ab cubed, that means the ab is going to appear 3 times. ab times ab times ab, which means altogether total there are 3 a's and 3 b's. This gives rise to the exponential property where if we've got a product raised to some power, we simply take each factor raised to that power. So a to b to the m is a to the m, b to the m. Similar thing happens with division. If we've got a over b cubed, that means it's going to happen 3 times. A over b times a over b times a over b, which means total we've got a cubed in the numerator and b cubed in the denominator. So what we can do is use the exponent property that a over b to the m power simply means we take the numerator to that power and the denominator to that power. Our 8th property is going to be similar to this fraction power, a over b to the negative 2 power. The negative exponent we know is going to move things around. So the negative exponent's actually going to flip this over to b over a squared. And then we know the squared means we take the squared on top and the squared on the bottom. This gives rise to the exponential property that a over b to some negative exponent is going to flip the fraction over, making it b over a, and then we take the exponent of m as a positive exponent now on both of them. This becomes our 8th property. Our 9th property is one that we've seen before. If we had something like 8 to the 2/3 power, we would recognize that the denominator on the exponent becomes the index of a radical. And then we square what's left. The cube root of 8 is 2, and we still have the squared. 2 squared is 4. This reminds us of the property that the mth root of a to the n is simply a rational exponent, where n is on top and the index of m is in the denominator. And depending on the context, we might use this property backwards or forwards. We might start with the fractional exponent and change it to a radical, or we might start with a radical and change it to a fractional exponent. One last non-rule that I want to remind us of is if we have a plus b to the m. The common thing we see students do is they will say that's a to the m plus b to the m. But this is not correct. If we were to FOIL this out, you'll find that we have terms in the middle that have been lost by doing the shortcut. So there is no distributing of exponents on terms. And if you remember, terms are things that are added and subtracted. So if there's any adding or subtracting in there, there is definitely no distributing of those terms. Cannot do that. So that was a quick, less than 10-minute crash course review of the exponent properties that we've seen before. Let's take a look at actually simplifying some expressions using these properties. And we'll start simple and we'll build to more interesting problems. So let's start with 5x squared, y cubed, to be multiplied by 2x to the 4th, y to the 5th. We know when we're multiplying, we can add exponents together. First, starting with the numbers, though, 5 times 2 is 10. Then on the x's, we can add the exponents. X squared and x to the 4th is x to the 6th. And finally, on the y's, we can add the exponents as well. 3 plus 5 is 8. And so we have our final solution, 10x to the 6th, y to the 8th. How about this problem? If we have 9, a to the 6th, b to the 5th, c, and all that's raised to the 1/2. Because we have factors that are multiplied inside the parentheses, we can take the 1/2 and put it on each factor. So we have 9 to the 1/2 power. Notice I did not multiply 9 by 1/2. Exponent rules do not affect bases. Exponent rules affect exponents. So we have 9 to the 1/2. A to the 6 times 1/2 is 3. B to the 5 times 1/2 is 5/2. C to the 1 times 1/2 is 1/2 power. Oops, my 9 disappeared on me. I want to take a quick look at that 9 to the 1/2 power because we can actually simplify that. If you remember, 1/2 power would be a square root, a second root of 9. And the square root of 9 is 3, so we can rewrite this as 3a cubed, b to the 5/2, c to the 1/2 as our final solution. How about this one? If we have 3a squared over 25 cubed times 5a over 3 to the 5th power. To kind of help us out with these numbers, because the numbers are going to get huge, we're going to keep them in their factored form. So for example, the 25, I can factor that to 5 squared. So now when I take the 3 in, I'm going to treat that as 3 to the 3rd, a to the 3 times 2, and 5 to the 2 times 3. 3 to the 3rd, a to the 6th, over 5 to the 2 times 3 is 6th power. That is going to be multiplied by taking the 5 through onto each factor, 5 to the 5th power, a to the 5th power, over 3 to the 5th power. Now we can start to combine things together. First, let's look at the a's. A to the 6th and a to the 5th, we know we can add those exponents and get a to the 11th. On the 3's, we have 3 to the 3rd over 3 to the 5th. Subtracting those exponents, 3 minus 5 is negative 2. So the negative exponent tells me to put the 3 squared in the denominator. The negative moved it down into the denominator. 3 minus 5 giving us 2. Similarly with the 5's, we've got 5th power minus 6th power is 5 to the negative 1 power. The negative says move it down to the denominator. And so when we simplify, our numerator is a to the 11th. Our denominator is 5 times 3 squared, or 5 times 9, is 45. And we have our solution. Let's try this problem. Let's do x to the negative 2, y to the 5th, all that to the negative 3 power. Before we do any moving of variables, we have to take care of the parentheses, taking this negative 3 onto each part. That's going to give us x to the negative 2 times negative 3, positive 6th power, and y to the 5 times negative 3, negative 15th power. Now that we've taken care of the parentheses, now we can move that negative exponent to the denominator. So we have x to the 6th over y to the 15th for our final solution. Let's try another one. Let's do 7x cubed y to the negative 2 over 14x to the negative 4 y to the negative 3. This problem does not have any parentheses. Rather than subtracting with all the negatives, though, and risk a sign error, let's move all of these negative exponents around. So if there's a negative exponent, it's going to move to the opposite location. So the 7x cubed stays where it is. The y squared moves down. The 14 stays where it is. The x to the 4th moves up. And the y cubed moves up. Now as we're simplifying, 7 over 14 is going to reduce to a 2 in the denominator. For the x's, because they're on the same line, we can add those exponents. 3 plus 4 gives us x to the 7th. For the y's, being on different levels, we'll subtract them. 3 minus 2 gives 1y. And because it's positive, it stays in the numerator. We have our final answer. Let's try another one. Let's try a to the 5th over 32b to the negative 1/5 power. I like to do negative exponents outside of parentheses in 2 steps. One step, the negative flips it over, 32b over a to the 5th, all to the 1/5 power. Then on a second step, I'll take the 1/5 onto each part, giving us 32 to the 1/5 power, b to the 1/5 power, over a to the 5 times 1/5 is just 1. Now we'll remember the 32 to the 1/5 power. That's like saying the 32nd, or 32 to the 5th root. And if we factor 32 into 4 times 8, 4 is 2 times 2, 8 is 2 times 4, 4 is 2 times 2, we notice 32 has 5 2's in it. It's the 5th root of 2 to the 5th power, which means that's just going to be a 2, as the 5th power and the 5th root will undo each other, giving us 2b to the 1/5 all over a for our final solution. Let's do one more interesting exponent problem. Let's do 3a to the 1/3 plus b to the 1/3 times 9a to the 2/3 minus 3a to the 1/3 b to the 1/3 plus b to the 2/3. Because of all the adding and subtracting in this problem, we're not able to use our normal exponent rules. We can't just add exponents on a and b. We can't do any of those tricks. Instead, with the adding and subtracting in the middle, we're going to have to distribute everything through. First, we'll take 3a to the 1/3 times 9a to the 2/3. 3 times 9 is 27. And on the a's, we can add the exponent. 1/3 plus 2/3 is 3/3, or just first power. Continuing to distribute, we have 3 times 3 is negative 9. A to the 1/3 plus 1/3 is 2/3. B to the 1/3. Continuing to distribute onto the third term, we have plus 3, a to the 1/3, b to the 2/3. Now we'll distribute the b to the 1/3. When we multiply by 9, we get a positive 9, a to the 2/3, b to the 1/3. And then when we distribute onto the -3, we get -3 a to the 1/3. b to the 1/3 plus 1/3 is 2/3. And finally, plus b to the 1/3 plus 2/3. Whoops. Plus b to the 1/3 plus 2/3 is 3/3, or 1. When we try to combine like terms from this point, some interesting things happen. We've got -9 a to the 2/3 b to the 1/3. We also have a positive 9 a to the 2/3 b to the 1/3. We also have a 3 a to the 1/3 b to the 2/3, and a -3 a to the 1/3 b to the 2/3, which means all that's left on this problem is the 27a and the positive b for our final solution. Now, all these problems we've seen thus far, you might have seen on a pre-college math course in beginning intermediate algebra. We've done problems like this before. Now at the pre-calculus level, we want to take this to the next step. And that next step is we're going to start to see variables in the exponents. The properties are still the same. The rules are the same. The patterns are the same. There's just going to be variables along the way. So this shouldn't be a big jump to try and simplify things like a to the n times a to the 2n minus 5 times a to the 3n plus 1 squared. Same patterns as before, we have to take care of the parentheses first. And when the 2 goes through parentheses, it has to multiply by the entire exponent. So the first factor is staying the same, a to the n, a to the 2n minus 5. And on the third factor, when we multiply by 2, we now have 6n plus 2. Next, we know that if the bases are all the same, which they are, we can add the exponents on a. And when we add these exponents, we'll combine like terms. N plus 2n plus 6n is 9n. The other like terms of minus 5 plus 2 gives us a minus 3. And we have our final solution, a to the 9n minus 3. Same patterns, just variables in there that we get to simplify along the way. Let's try another example. Let's do 5b to the n plus 2 squared over b to the 3 times n minus 1 times b to the n over b to the n to the 5th power. Again, we need to take care of the exponents first by putting the squared onto each factor. So we have 5 squared, which is 25. B to the, we're going to multiply the entire exponent by 2. That's going to give us 2n plus 4. Over b to the, we might as well distribute, 3n minus 3 times b to the n over, again we multiply as we go through parentheses, b to the 5n. Simplifying a bit, let's go straight across. We've got several options, but I'm going to go straight across. We've got 25b to the 2n plus n, combining like terms, is 3n, and we still have a plus 4, over b to the 3n plus 5n is 8n minus 3. Then when we subtract exponents on the b, you'll see on the ends we've got 3n minus 8. That's going to be negative 5n. Hyperactive scroll. 3n minus 8n is negative 5n. And then 4 minus, be careful here, we're doing 4 minus negative 3. Minus a negative 3 makes it a positive. 4 plus 3 is 7. Be very careful of sign errors there. And to make this nicer, we don't like to see negative exponents, so I'm going to write this as b to the 7 minus 5n. Switching the order there so the first part of the exponent is positive, and then we can leave it like it is. So 25b to the 7 minus 5n. Let's try another example. Let's see if we can come up with a couple good ones here as we start to wrap up. We've got x to the m over y to the n squared times x to the 3m over y to the 2n to the negative 2 power, and then we're going to cube everything. So let's simplify from the inside out. Taking the 2 through onto both parts is going to give us x to the 2m, y to the 2n, times, taking the negative 2 through, we get x to the negative 6m over y to the negative 4n. All that's still cubed. But let's keep working on the inside. We can combine the x's and combine the y's by adding the exponents. 2 minus 6 is a negative 4m. Over y to the 2 minus 4 is negative 2n. And all of that is still cubed. We can do this at several points along the way. We might as well do it now. Take care of those negative exponents by moving them around, giving us y to the 2n on top and x to the 4m in the denominator. All of that is cubed. And so when we cube, don't want to lose my problem at the top. When we cube both parts, we get y to the 2 times 3, or 6n, over x to the 4 times 3, or 12m, and we have our final simplified solution. Let's try another. Let's do x to the 5n plus 1, y to the negative n plus 2, over x to the negative 3n plus 1, y to the 3n plus 2, and all of that to the 1 over 4n power. Let's start by simplifying our x's. When we do, we're going to subtract the exponents, 5n minus a negative 3n. Be careful there, we're subtracting a negative. 5 minus a negative is the same as saying 5 plus 3, which is 8n. And 1 minus 1 is 0. On the y's, if we start with the negative n and subtract 3n, negative 1 minus 3 is negative 4n. And 2 minus 2 is 0. And then we've got all that to the 1 over 4n. Let's go ahead and fix that negative exponent and move it down at this point. X to the 8n over y to the 4n, and all of that is to the 1 over 4n. When we take that exponent and put it on both parts, we get x to the 8n over 4n. Well, 8 over 4 is 2, and the n's will divide out, over y to the 4n over 4n, which is just 1. And so for our final answer on the exponents, we have x squared over y. Let's do another one with these fractional exponents in them. How about x to the 1 over 3n, x to the 1 over 6n, over x to the negative 1 over 2n, and all of that to the n over 2 power. This time I'm going to fix that negative exponent first. Let's get them all on the same line. X to the 1 over 3n, x to the 1 over 6n, x to the positive 1 over 2n, to the n over 2. One thing I'll notice is in order to add these exponents, we're going to need a common denominator. All the denominators have n, so we'll look at the 2, 6, and 3. Common denominator there is going to be 6. So we're going to multiply by 2 over 2, 1 over 1, and 3 over 3. And that's going to give us x to the 2 over 6n times x to the 1 over 6n times x to the 3 over 6n to the n over 2. Now we can add them together. 2 plus 1 plus 3 is 6. So we have x to the 6 over 6n, and if you divide out the 6's, we get 1 over n. But that is still to the n over 2 power. When we multiply those, the n's will divide out, and we're just left with x to the 1/2 power. Or we could change that to a radical if we wanted to as well. Both answers would be correct. The square root of x. Let's do one last problem as we wrap up these exponent properties. Let's say we've got x to the 3n plus 1, y to the 1 minus n, over x to the 2n plus 1, y to the n plus 1. And we're going to throw in a divide. And we're going to divide by x to the 3 times n minus 1, y to the negative 3, over x to the 3 times n plus 1, y to the 3 minus 3n. And we're going to take all of that to the n over 2 power. This is a great problem, mixing together lots of different exponent rules. Let's start with the first one and the x's. When we subtract exponents, because it's division, we get x to the 3n minus 2n is 1n, and 1 minus 1 is 0. For the y's, let's actually do it in a different color. For the y's, we're going to subtract those exponents. For the n's, we have negative n minus n is negative 2n. 1 minus 1 is 0. Divided by, what can we simplify on the right side? Well, if we distribute our 3's through, that would give us x to the 3n minus 3 over x to the 3n plus 3. For the y's, when we subtract those exponents, we'll just put them on top, keep them positive. Negative 3 minus 3 is negative 6 minus 3n. And all of that's still to the n over 2. So the right side's going to require a little bit more work. The left side's essentially done when we move the negative exponent. So we've got x to the n over y to the 2n divided by whatever we end up with on the right side. Let's look first at the x's. 3n minus 3n is 0. Negative 3 plus 3, I'm sorry, we're subtracting because of the division. Negative 3 minus 3 is negative 6. And then we still have the y to the negative 6 minus 3n. All of that still to the n over 2 power. Let's make those negative exponents positive. So we've got x to the n over y to the 2n divided by 1 over x to the 6th. And when we move the y down, we have to change both signs. This is very important that both signs change. Positive 6 and a positive 3n. All to the n over 2. Still simplifying on the right side because that n over 2 has to go on to each part. So the first fraction unchanged, x to the n over y to the 2n, divided by 1 to any power is 1, over x to the 6n over 2, that's going to be 3n. The n over 2 goes on the whole thing here, so that's going to be 6n over 2, which reduces to 3n, plus 3n times n over 2 is 3n squared over 2. Finally, how do we divide fractions? We multiply by the reciprocal. So we're going to multiply by x to the 3n, y to the 3n plus 3n squared over 2, all over 1. Now we can add the exponents on the x's. 1n plus 3n gives us x to the 4n. For the y's, we'll subtract the exponents. Subtracting 3n minus 2n gives us y to the n plus that 3n squared over 2. And we have our final solution. We've got about 10 properties about exponents that we started with at the beginning. All 10 should have been a review of what we saw in previous math classes. Today what we're doing is reinforcing those concepts, practicing using those exponential properties with variables and the exponents on occasion. The homework set has several great examples that you need to practice working through, making sure that you master simplifying these exponents. Thank you for watching the video.